Today we're going to cover the type of unloading device is known as end deactivators. Now, first thing, just a little bit on nomenclature here, or wording. Often, throughout the industry, people just call these unloaders, which is a generic term. Unloaders is just anything that unloads the compressor in terms of horsepower or flow. Both clearance devices and end deactivators technically would both be unloaders. So it does get a little confusing in the field that if we call everything unloaders, we don't specifically identify what type. A couple weeks ago, we talked about the clearance space, the front head clearance pockets, the valve cap pockets, the internal body pockets, and clearance being the best way to unload a compressor in terms of efficiency. Today, we're going to talk about other methods in deactivation. Every one of these has pros and cons. So we'll talk about.
I lost Dwayne.
Can you guys hear me?
I'll still hear him. You came back, but you were gone for a moment there, Dwayne, on my end.
Okay. Hopefully everyone's hearing me. I'm not getting any network messages.
I'm hearing you.
Okay. So we'll talk about a second method here called end deactivation. Like I said, all of these types of devices have pros and cons, and we'll talk about the pros and cons of end deactivators toward the end of today's presentation. So let's go ahead and get started. The first thing to keep in mind about end deactivators is how they distort the PV card. So if you remember from a couple weeks ago, the standard PV card is what you see in the gray dotted line. That is over here on the right-hand side, we have the compression event where we compress the gas up to the top here. The internal pressure now exceeds the discharge pressure on the backside of the discharge valves. The discharge valves start to open. We push the gas out through the discharge valves. By the end of the stroke, we pushed out pretty much all the gas, a little bit left. The piston turns around and starts traveling the other direction. The volume increases and hence the internal gas pressure falls. That becomes the expansion event. The piston moves back so far that the internal pressure falls so far that it goes lower than the suction pressure on the backside of the suction valves. So therefore the suction valves now open and new gas flows into the compressor cylinder, and we repeat the cycle. Some of the things we talked about a couple weeks ago, namely the area inside of that PV card basically corresponded to the amount of power required to compress the gas. From the blue line up to the red line inside the PV card was how much power it takes to compress the gas completely. The area between the red and the top was the discharge valve loss, how much power to get the gas through the discharge valves. And between the blue line and the bottom curve was the suction valve loss, how much power it takes to pull gas through the suction valves. Altogether, that was your total horsepower for that cylinder end in terms of indicated horsepower, which the PV card doesn't have anything to do with friction losses. However, now when we look at an end deactivator, how it does, it distorts the PV card by making it look more like a flying saucer or a pair of lips. Okay. So, but we still have area inside of this PV card, which now means there's still associated power required, horsepower. If we look at the suction volumetric event, it goes all the way across, so it's 100%. We pull in, during the entire time we're pulling in gas. However, when we go to move the piston the other direction, we're pushing suction gas out the entire time also. No gas actually leaves the discharge valves. So there is power associated with this end deactivation device. However, there's zero flow going out the discharge valves. Now, at first, it doesn't make any sense. Why would I burn up energy and get no flow out of it? But this goes back to what we talked about a couple weeks ago, namely that semi-truck with a big heavy load on it trying to get up a hill. If it tried to stay in one gear, it's going to burn up the engine trying to go up that steep hill, and it's going to stall out and obviously never get up the hill. But if it can downshift and go into different gears, they can handle the torque better. But it takes the truck longer because it now goes slower. It can eventually get up the hill, accomplish its goal, and move on. Same thing with the end deactivators. originally, we talked about the clearance devices. We added more clearance, which made this background TV card skinnier. And I'll bring that up here real quick, just to remind everybody. So this was the TV card from a couple weeks ago, and as we added clearance, if you remember, it made the card skinnier. Wider card, more horsepower; skinnier card, less horsepower. But now when we go to deactivate the end, we get something like this. Certain amount of horsepower is still associated because we have area, but no flow going through there. That simply gives us another way of unloading. Now obviously, if you only had one cylinder end on the compressor, you're burning up energy and getting no flow. But if you think of like a four-throw compressor, a four-throw compressor has 8 ends. If we just sacrifice one of those ends, having no flow going through one of these ends, well, that's about a 1/8 or 12% change in flow, but the other 7/8, 88%, are still flowing gas. So if that's the price we have to pay to keep the compressor running, sacrifice one of the ends, it's a better deal than trying to burn up the engine because we can't unload it at all. Okay. So now, with that, a little bit of information here on the TV card, how it looks, what type of devices or ways can we deactivate compressor cylinder ends? The first way is the most obvious, and they've been doing this since the day first compressors probably ever built, and that is normally there's a suction valve here. It's a one-way valve. The gas goes through into the cylinder end. When the piston goes this way, it can't push the gas back through a suction valve, so it has to compress the gas and push it through a discharge valve. But if you were to completely remove that valve altogether, or at least take out the plates or the pockets, then gas would free flow into here because there's just holes left, free flow into here, and then when the piston moves the other direction, it's just going to push the gas right back up through the suction valve. So pulling valves is a very common way of doing it. Often you'll see these in gas gathering. As the compressor hits a certain limit, they shut down, pull the valves, and start it back up with these valves removed. Drawback, obviously, here is you have to shut the compressor down, open up the valve cover, remove the valve, or put the valve back in, depending which direction you're going. Every time you do that, you got to purge all the gas out of here, put in or remove the valve, purge it back up with gas, and then get the unit started again. Obviously, with methane emissions and all that, losing all the gas to atmosphere, not only are you losing money, but, you're causing emissions and so forth. So it isn't the most efficient or environmentally friendly way, but it's very cost effective because you're just shutting down, removing, or replacing the valve and starting back up. Okay, now, so that's a simple way with no device at all. You're basically just removing the valve. In regards to actual devices, we'll hit a couple of older ones. The first one here is something that's actually designed and built into the cylinder. Namely, it's a certain plug here, and there's a port here. Now, this has got another plug going in here, filling up the space. But if you remove this plug here, you can have an actuator or a plug going across here. And what that would do is free open this plug here and flow the gas right back through this hole. So the valve's over here separate. So this is a separate hole going into the cylinder all by itself. The advantage here is you're basically opening up a hole inside of the cylinder for the gas to free flow without having to affect one of the valves. However, this only applies if the cylinder was designed and built with this type of porting into the cylinder itself. These are relatively rare, not that many cylinders have them, but if they do, it's a convenient and efficient way of deactivating the cylinder end. Another way, this is just a zoomed in section of that so you can see that porting a little bit better. Another device that we see is known as a valve lifter. Now in this case, we're showing a mechanical one here, but there's a turn wheel up here, threaded down, going through here to the valve. And what it's actually going to do is, here you can see part of the valve. As we turn the wheel, it's going to lift that valve plate up or push it down, to either cause a gap going around it or to push the valve down so now the gas has to go through the valve. So just a mechanical way of lifting the valve up, getting it out of the way, exposing flow directly in and out of the cylinder, or sealing the valve back down. These had some issues, obviously. That valve probably wants to wobble back and forth and get vibration and resonance and so forth. So you don't see too many of these anymore. But that was one approach. Okay, another way that's fairly common is what's known as finger-type valve unloaders. And these are the default you'll tend to see on like aerial compressors. Bicker makes a lot of these standard for aerial unloading. Now ACI would love to replace all these with like radial valve unloaders. But one of the advantages of a finger-type unloader is it's on the back side of the valve, which means it doesn't really add a whole lot of fixed clearance on the inside. Now the way that this works, basically, is you have an actuator up here, and these metal fingers will push down on the valve plate so that the gas can free flow around the valve plate. So instead of the valve plate responding to pressure differential, suction pressure on one side and internal cylinder pressure on the other side, causing it to open and close, now it's going to physically be pushed down and held down by these fingers. So if they're held down all the time, it doesn't matter what the differential pressure is. Gas is going to free flow around them all the time. The advantage of these would be they don't really add hardly any fixed clearance to the internal cylinder. One of the drawbacks is you now have all this additional metal impeding the gas flow trying to get through the valve. It usually makes the valve a little bit less efficient. And then there's also another concern that, these are long metal fingers. You get stuff in the valve passageway, comes down through here, slugs the liquid perhaps. And if one of these metal fingers breaks, well, the gas is flowing this direction, which means if one of these fingers breaks, there's a possibility it can get pulled into the cylinder itself. Again, all these pros and cons. A common method that ACI has done for 60, 70 years now is a plug-type unloader. These go over the valves. So here, I'll zoom in on this here in a second. I'll give you a chance to read this. But I'm going to show an open state and a closed state. But basically, there's going to be a hole in the valve over here. And the actuator will be able to lift up or seal down this plug. And what that will do, so if I zoom in here, if the plug is open, gas is going to free flow through this opening in the middle, through these holes here. So we're in the gas passageway, now we're in the cylinder. Completely open hole, the gas is always going to take this route no matter what. However, if the actuator seals this plug down, now the gas can only go through the holes here from the gas passageway, through the plates or the poppets, depending what type of valve it is, into the cylinder. And because these are now one-way valves, gas can't come back through here, and because we're sealed over here on the plug, gas can't come back here. So this would be for a normal acting mode of the cylinder. This would be where we deactivate that end using this type of plug type in deactivator. Okay, another way that ACI offers, or at least another device that ACI offers, is what's known as a radial valve in deactivator. What this is has radial valves that are on a cage here. And that cage, that whole assembly can lift up and move down. What you'll see here is those little blue poppets are seated in their holes right now. So they're going to act just like a poppet valve. They're going to open and close based upon pressure differential. But if you move this entire cage assembly up, it's going to pull these poppets out of their holes and expose all of those holes as just free open holes for gas to flow in and out. Now, I do have a short little video here, and hopefully this plays okay through the WebEx. And it should give you an idea how this works. So if it's coming through okay, what you should see is those blue poppets being lifted up, opening that passageway there, and then coming back down, sealing that. Now it's going to rotate a little bit, and then we're going to dissolve the outside cover so you can see the inside mechanism work without that metal shield on the outside. There it goes. So now you should see that assembly lifting up and down. The advantage of this is it offers a lot more free flow area, both when it's a regular valve and when it's a deactivated, in its deactivated mode. One of the potential negatives on this is if I were to rotate it here, and if you look up through the middle, there's a large cone volume here that's all going to be added fixed clearance going up through the center here. Now, ACI can try to minimize that a bit, but it's still going to add more fixed clearance than some of the other devices might. Now, sometimes the cylinder is already relatively inefficient because it's in some type of process or some type of low ratio application or heavy gas, or the cylinder is maybe not perfectly the best type of cylinder for the application. Whatever the case is, the valves may already be inherently inefficient. They may be difficult to access the valves. It may be a situation where the operators don't want to mess around with the valves very often. So there is another way to deactivate a cylinder other than having something over the valves themselves. And ACI calls that a head-end bypass system. We have a couple of versions of that, a simplex and a duplex. But typically what it does here, it's going to open up a hole on the front head and via a plug. And when that is open, it'll allow the gas to free flow back and forth between the suction bottle and the cylinder front head here. Now, the advantage of that is it doesn't put anything over the valve, so we're not degrading the valves in any way. The drawback there, obviously, is you have some additional piping coming back here and so forth. What I'm going to do now is show a quick little animation. I thought, maybe not. I thought I had an animation on that. Apparently I don't. So the two variations there one is to open up a plug here and allow the gas to free flow back up to the suction bottle. Or the other is if the bottle's been out there and this is a retrofit, then what it can do is instead of going to a bottle, so that we don't have to cut a hole in the bottle and have to hydro test it in the field or x-ray it in the field or something, you can just have that piping come back up over to a valve cap. Either way, we're taking gas from the inside of the cylinder and porting it back up into the suction gas passageway or up into the suction bottle itself. But either direction you go, it basically prevents the gas from compressing inside the cylinder, and hence, we're not going to get any discharge gas going out. Okay? So there's a variety of different ways of deactivating cylinder ends, either from pulling the valves, putting stuff over the valve, like the fingers or the plug type unloaders, or having stuff off the front head, like a head-end bypass here. Now, some of the pros for end deactivators are namely, they generally involve larger steps of unloading. So a couple of weeks ago, we talked about the clearance pockets, and you could size the clearance pockets, having small volumes or large volumes. An end deactivator, you deactivate the entire end or you don't. It's an all or nothing type approach. Now, again, if you imagine if you had just a two-throw compressor, you have two cylinders, let's say they're both first stage, two cylinders, that's 4 ends. If you knock out one end, that's 25% roughly. So you can imagine when you look at load step curves and so forth, if you deactivate one of these, you're going to get a 25% step down typically in load or flow. That's a large step. So often what will happen is we'll mix these together with clearance pockets. We'll use clearance pockets for the 5% load step changes, and when we run out of clearance pockets, then we'll engage one of these end deactivators for a large step. And then ideally, we can then often reuse the clearance pockets. So you have small steps, and you max that off with one of these large steps, and you go back and use the small steps again. And by doing that and repeating that, you can get a nice series of unloading step curves. So it allows you to have large steps of unloading, often reuse your clearance pockets because we made a large step. Now we can go back, close all those pockets, and reuse them. The other thing that's nice about end deactivation is it's useful for both high, medium, and low compression ratios. When we saw the clearance devices before, clearance devices were ideal for medium ratios. They did not do very well in low ratios, and they were very suspect to issues like low volumetric efficiencies at high ratios. And just like clearance pockets, in deactivation devices are usually fairly easy to automate. Some of the cons with in deactivation, again, what was a pro over here can also sometimes be a con. That is, it does create too large of a load step, too large for the engine to handle, so sometimes we can't use them because of that. Another thing about in deactivators is that they are, if you install these on a compressor, they are more likely to lead to issues with pulsations, torsionals, or acoustic issues. So the first time you decide you need to put one of these on, if the unit's never had it, that unit needs to go in and have another acoustic pulsation study done and a torsional done to make sure that we're not going to kick up any issues, we're not going to break any crankshafts, stuff like that, just because of the way it distorts the forces acting on the crankshaft and or gas forces going in and out of the cylinders. Okay. To accommodate or reduce those pulsation or acoustic issues, it's also likely that sometimes the acoustic review will suggest that they need to have more restrictive orifice plates near those cylinder flanges. If you put an orifice plate near the cylinder flange to reduce those acoustic or torsional or pulsation issues, it's likely going to lead to a pressure drop. So now we decided we needed large steps, so we put in an in deactivator, and that ends up causing us to have, instead of a 2% pressure drop, now we have a 6% pressure drop, which reduces our flows quite a bit. So we have to be careful there, and that's where whoever the packager is or whoever's working on this, if you never had in deactivators and you put them on, we need to do some studies, and we need to probably oversize the flow a little bit, knowing that the acoustic study is going to require some restrictive devices, which is going to choke the overall flow back down some. The biggest con with an in deactivator is just the fact that it's not efficient. And that's going back to this simple PV card. There's always horsepower associated with that in deactivator, but there's always zero flow, which means you're always burning up energy and you're not getting any flow out of that. Now, the best thing to do there is try to make that as efficient in deactivation as you can, so you minimize your wasted horsepower. But if you're using a very inefficient in deactivator, you're going to burn up a lot of horsepower for zero flow, versus an efficient in deactivator, which is going to burn up a lot less horsepower for the same zero flow. So that's one thing. That's one thing. Sorry.
So Dwayne, that's why a lot of times we'll put more than one device in.
Right. So if you had a cylinder with 3 valves per corner, OEMs will generally put one on all 3 valves when they go out the door. ACI, if we retrofit something, you love to sell 3, but does the end user actually need 3? If they do, we have to put 3 on there. But if we can get the valve losses, with the in deactivation down, with only using 2, hey, that works for the customer. We got their horsepower down, and we kept the price as low as we could get it. But if you only had 1 out of the 3, then their overall losses may be really high. They're paying for this every day. They only pay for the in deactivator once. So if you double it to 2 and you can get this down, it's going to pay for itself within a few weeks or even days sometimes. Okay, and that's all I have for in deactivators. Any questions?
Dwayne, I guess I have a comment. A couple of things. One, when an end is deactivated, I don't know that it was clear that a volume pocket on that end that is deactivated would not put a device on the opposite end would. I don't know if that was clear when you stated that. And then the other thing with finger unloaders, those narrow fingers they come in contact with the valve plates, and those are typically moving. Even at 300 RPM, that's 5 times a second, and at speeds up to 1800 RPM, that's 30 times a second. So that's why finger type unloaders tend to fail more often.
The fingers here should hold the plates down and ideally would not move. Now, like a hydrocom, they would be moving, but these ones should hold them down. But Jeff's right. I mean, the gas forces are still going to put some pressure on these plates, and the plates are going to bend a little bit. And obviously that's going to push back on this hydraulic a little bit. So you may get some motion a little bit if there's not enough hydraulic force to keep them held down tightly.
Well, what I'm pointing out is when you engage it, those plates are moving, and those fingers have to contact those pieces that are moving. And that's why valve plates break and fingers break.
So when the plates are responding to the normal gas opening and close, because these fingers are physically attached to these plates in some cases, this whole assembly is moving up and down with it during that time.
And so just so everybody's clear, ACI's position is we do not manufacture or typically recommend finger type unloaders because the valve area is a highly maintenance area, intense area anyway. So we feel it's kind of silly to put something that breaks more easily and kind of complicates the valve pocket itself. So ACI does not design, manufacture finger type unloaders. We will recommend them on aerial units in some cases because particularly on smaller valves when we can't fit our plug type deactivator in there. But for the most part, we will recommend, do anything we can to recommend against the finger type unloader.
Here. I can use that one. Let me see. So if we come back to this one here, I can zoom in on this. Okay, so Jeff made a comment. So the end deactivators can go over the suction valves here on the head end, which is the most common location for them. However, there are times people will put end deactivators over crank-in suction valves. Now, the reason they may put them over the crank-in suction valves is because the most common place for a clearance pocket is over here off the front head. Hopefully you're seeing my mouse move. Has everyone seen the mouse move? Or not? Oh, okay. So by having the end deactivators over the crank, we deactivate the crank-in section, but the head end's still compressing gas, which means this clearance pocket out here can affect it. However, if you deactivate a head end, it doesn't matter if this clearance pocket's open or closed because the gas is just free flowing through this valve here. The pocket has no effect anymore. When we saw the flying saucer type shape, you can add all the clearance in the world. It's not going to distort that flying saucer type shape. So now the drawback with putting end deactivators on the crank-in is we have to be careful because if you deactivate a crank-in, we change the forces back here in such a way that we are significantly more likely to get into rod load issues and or pin non-reversal issues back here at the crosshead. It's not to say it happens all the time, but it's just significantly more feasible or possible that it's going to happen if we deactivate a crank-in. Now, the other thing that can be done is while the end deactivators will generally go over suction valves, there are some cases out there that we put end deactivators over discharge valves. And that is to overcome rod loads or such because we either need high forces, high gas pressures, either on the crank-in side or on the head-end side to make sure that we stay out of rod loads. But those are very rare, like less than 1% of the time. The most common place generally is going to be over suction valves on the head end. Second most common would be over suction valves on the crank-in. Okay. That was a good point. Any others? Okay. If you had any, you might have been on mute because I didn't hear any. Okay, that's all I got for today. Hopefully, there's a little bit of insight there onto Deactivators. Hopefully, everyone have a good day today. Thanks, everybody. Thank you, Dwayne. Hey.
Thanks, Dwayne.
Bye.